Hello and welcome to this physics video, and in honor of the launch of the Falcon 9 SpaceX vehicle today, May 30th, 2020, I've got my space up in the background. This is a video on the second law of thermodynamics in chapter 20 on the second law of thermodynamics. And I'm following the basic order of topics in Young and Freedman's University physics. This is not a math section. It's more of an informal presentation of two versions of the second law of thermodynamics. The one thermodynamics. The first one is the engine statement, the heat engine statement, which basically it says you can never completely convert heat into work. Second law of thermodynamics. Some of it's going to be lost as entropy, as unrecoverable heat. The second statement of the second law of thermodynamics is the so-called refrigerator statement, which is the basic idea that heat never flows spontaneously from cold to hot. It always spontaneously goes from hot to cold. Well, let's go into a little bit more detail on these two statements, informal-ish statements of the second law of thermodynamics. So let's look first at the engine statement, the heat engine statement, or the Kelvin-Planck statement of the second law of thermodynamics. So basically, if you remember from previous videos in this chapter on the second law of thermodynamics, that you always have some heat loss. The heat engine is usually a circle. I should have drawn a circle here. You always have some loss of heat. You can't have 100% of the heat in the heat engine go toward W, toward work. Just simply won't happen. Or here it is in a little bit more formal terms. It is impossible for any system to undergo a process in which it absorbs heat from a reservoir at a single temperature and converts the heat completely into mechanical work. There's always going to be some loss, with the system ending in the same state in which it began. Okay, so this is the Kelvin-Planck or engine statement of the second law of thermodynamics. Okay, what is basically going on here? Well, in a moving body, let's say you have a body moving forward, or let's say you have, let's say I'm walking across the floor or something like that. You've got internal energy in, let's say I push a brick across a floor. You've got the kind of random motion of stuff inside the brick, the internal energy, as it were, of the brick. You have that, but you also have the coordinates. That's random motion. You also have the coordinated motion of the brick moving forward because I've pushed it. So you've got coordinated motion and you've got random motion. Well, the kinetic energy of the body itself has to do with the coordinated motion going forward, and we know this 1/2 mv squared, as it's moving forward. But the other kind of energy is this random energy, which is inside the brick. The internal energy of the brick is the sum of all the kinetic and potential energy within the brick itself, of the random motion. Now here's the kicker. Energy that is transferred from the coordinated motion to the random motion, you just can't recover. You can't fully get that back, and that is the loss in the second law of thermodynamics. Okay, so that's the engine formulation. The other formulation is the refrigerator statement of the second law of thermodynamics, or the Clausius statement of the second law of thermodynamics. If you remember in our video on refrigerators, there has to be work coming in here from the side in order to pull heat out of one body into a hotter body, from a colder body to a hotter body. In order to do that, you've got to have some work coming in here. It's not going to happen spontaneously, and it's not going to all be recovered. Or to put it a little bit more formally, it is impossible for any process to have as its sole result the transfer of heat from a cooler to a hotter body. There's going to have to be work done in order for this to happen. Now, these two statements, the engine statement and the refrigerator statement, are roughly equivalent. Because if you could have an engine that was 100% efficient, you could run that engine by bringing up heat from the cold reservoir be, okay, let me pause for just a second, get my head together. Okay, let's try that again. If you could have an engine that was 100% efficient, you could run that engine by using heat from the hot reservoir to power a refrigerator with no net work done. In other words, it'd be a nice little cycle with no outside work needed done. You could have the heat power the refrigerator that would then come back into the heat, and it would go round and round. But that would violate the refrigerator version, because you can't get heat out of a colder into a hotter without work from the outside. Now, if you could have a workless refrigerator, you could run an engine on it. You could bring up the heat and run the heat engine, which would violate the engine version. And there's some diagrams. There are two diagrams in this section that basically show you what is impossible. But I think it's pretty easy to get, is that you cannot 100% convert heat into work, and you cannot 100% get something from cold to hot without external help. So finally, the conversion of work to heat, the flow of heat to cold, the free expansion of gas from high to low pressure, the free mixture of gases and mixable liquids, these are all irreversible processes. They only go in one direction unless you can, it's going to take work, external work, in order to reverse anything of this sort. And a lot of it is unrecoverable. So a final thought in this video. The first and second laws of thermodynamics are not entailed by each other. They actually are, in a way, two separate laws. The first law of thermodynamics basically says that you cannot create or destroy energy. Fine. The second law, though, doesn't have to do with creating or destroying energy. It has to do with the availability of energy and how you can use energy. So in a sense, they're both laws of thermodynamics because they have to do with thermodynamics, but they are not actually connected to each other in what they are about. And that is a somewhat informal look at the second law of thermodynamics.